Hi, my name is Erin Choi, a PhD student at KAIST in Korea. Today, I will presenting our paper titled Text Breakpoint Generation using Origin-Centric Graph in Virtual Reality Recordings for Adaptive Playback. Let me start with a brief overview. We record assembly scenario in virtual reality as continuous spatial videos. Then we automatically generate task breakpoints to segment each recording into fine-grained and coarse-grained units. This creates task-level structure that can later be used to support adaptive playback and navigation. Now, let me explain the motivation. In AR and VR, recorded task tutorials can make training more scalable by reducing the time and effort required from expert. VR tutorials are especially powerful because learners can watch demonstration immersively at a one-to-one scale from any angle and distance. However, the playback speed of a recorded video often doesn't match the learner's pace. So in an ACMD setting, playback should adapt to the user's current progress and proficiency. To do that, the recording must be segmented into meaningful steps, similar to YouTube chapters, so user can repeat specific segments or adjust playback speed. But this is much harder in VR spatial video because it includes rich 3D interaction beyond 2D footage. Moreover, existing VR recording methods often don't preserve the interaction and state information needed for reliable segmentation. So the key question becomes, how should we record and segment tasks in VR to support adaptive playback? Next, I will cover related work in three areas. First, AR/VR tutorials recording helps, but manual step segmentation is costly. Second, task segmentation. Most methods are 2D and fine only, so they miss hierarchical structure. And the third one is spatial video recording. We need 3D interaction aware structure recording, not just image. Before diving into the method, we define a task breakpoint as a cognitive transition point during task execution, marking the boundary of a meaningful unit that can support adaptive playback. Next, we ran a preliminary study to derive breakpoint criteria and understand what information is needed for adaptive replay. We used an IKEA chair assembly scenario. First, 4 VR experts recorded the task using a Metacast 3 and Unity, capturing 60 of hand and object data at 60 fps. Then 12 user annotated both fine and coarse breakpoints with the video order counterbalance using a Latin scale design. Based on the breakpoint identified by user, we analyze their annotation along with interview feedback. We find 3 recurring segmentation triggers. T1 integration, a part attached to the structure core or origin. T2 centrality, a connection moves closer to the core, updating the center object. T3 topology, a new subassembly or new group begins to form. This insight also guided our data structure design. We use a single representation that captures relationship explicitly. Nodes are hands and object with 60 OF, and edges are hand adjacency and object adjacency. This structured recording enables us to extract fine and coarse breakpoint units. As shown in the video, we record the task using a frame-by-frame scene graph. Then, based on the fully assembled final graph, we infer the overall structure. We define an origin-centric graph, select an origin object, and capture relationship based on each object's distance from the origin. We select the origin object as the node with the highest degree centrality. In other words, the part with the most connection in the final assembly. Then we compute an origin-centric weight from each object based on the shortest path distance from the origin. So objects closer to the origin receive higher weights. Based on this representation, we generate task breakpoint using three rules. First, direct connection to origin derived from T1 when a part or subgroup connects directly to the origin as shown in figure A. Second, central object updates derived from T2 when a new connection changes with which object is most central in the active group as in figure B. Third, subassembly formation derived from T3 when a new group starts forming away from the origin, indicating a distinct subtask as in figure C. Next, we generate coarse breakpoints by merging consecutive fine units that shares the same central object or involve repetitive action of the same category, including two operations, and we keep only the final timestamp. Then we refine the breakpoint to the moment the user actually finishes the action by shifting it to the first frame where the hands release the object involved. As you can see in the video, coarse breakpoints corresponds to major contextual change, such as shift in the overall task situation or goals. In contrast, fine breakpoints capture specific detail, action, or sub-goal transition. To evaluate our method, we collect user segmentation data and treat it in ground truth. Since our goal is to automate how users would naturally divide tasks into meaningful units, we ran the study on two VR assembly recordings, drone and bicycle, representing complex and simple tasks. On the left table, we summarize the breakpoint user selected. For example, user marked more fine breakpoint in the drone task, and we cluster the annotation to obtain GT breakpoints for both fine and coarse levels. On the right table, we compare our detected breakpoints against that GT using MAE or MSE precision, record, and endpoint score. Using a 3 seconds Holoris window, our method achieves high endpoint score for fine break points in the bicycle task, while coarse breakpoint also remains strong. This test story shows screenshot at our detected breakpoints. The segments capture meaningful moments, such as when key parts are assembled. And this figure visualizes the table result. Comparing our breakpoints with the GT, you can see they align closely and almost overlap. Overall, these results give us 5 takeaways. First, reliable VR replay. Our scene rep recording preserves hand-object interaction for multi-view playback. Second, a CG clarifies structure. The origin-centric representation captures task hierarchy and key transition. Third, high detection accuracy. And for two-level utility, fine units support detailed guidance, while coarse units provide a workflow overview. And finally, acceptable timing error. Our timing differences stay with typical user annotation variability. Now, let me just discuss limitation and future work. First, we validated our method on the assembly task. So future work is to extend it to the broader task domains. Second, our evaluation is based on GT matching, and end user outcomes are still untested. So we plan to evaluate with end user using adaptive playback. So this is a VR only study, and deploying in AR will require robust tracking. So we will extend the method to AR recording scenario. To wrap up, our work delivers 3 outcomes. We provide a recording pipeline that captures user-object interaction and task progress in VR. On top of that, STSG, OCG, let us extract hierarchical breakpoints, fine and coarse, directly from raw interaction data. Overall, this reduces the cost of manual segmentation while maintaining strong agreement with user-perceived task structure. This is end of my presentation. Thank you.